I think now I will turn it like this way.
Professor U. Kamachi Mudri, Honorable Vice Chancellor, Homi Bhabha National Institute, Dr. P.D. Naik, Dean, Homi Bhabha National Institute, Dr. Devashish Bhattacharya, Chief Guest for today's function, Dr. Raghavendra Tiwari, Associate Director, Materials Group. Dear friends, ladies and gentlemen, a very good afternoon to all of you. Today we have assembled here to celebrate National Engineers Day. National Engineers Day is celebrated on September 15th every year to mark the birth anniversary of Sir M. Visvesvaraya, a renowned Indian engineer and statesman. Already we are running a little bit behind schedule. Without wasting much time, I request Professor P.D. Naik, Dean, Homi Bhabha National Institute, for the welcome address. Thank you. Please, sir.
Good afternoon to everyone, and I thank all of you for joining the HBNI Engineers Day Celebration Function 2023. I, P.D. Naik, on behalf of Homi Bhabha National Institute, and my behalf, welcome you all for this function. In fact, many dignitaries and participants have joined online. I welcome them for this function. We feel extremely honored by the presence of Dr. Devashish Bhattacharya, Vice President, Technology and R&D, BRC Limited. Thanks, sir, for accepting our invitations to be chief guest for today's functions and also agreeing to deliver a chief guest lecture today. We have with us Professor U. Kamashi Mudari, Honorable Vice Chancellor, HBNI. Professor Raghvendra Tiwari, Convener Board of Studies, HBNI, and Associate Director, Materials Group, BRC. Thank you, Raghvendra, for organizing these functions at D Block and making all arrangement for visit of chief guests to various facilities at BRC. We have online Professor Arvind Dover, Founder Director HBNI and Emeritus Professor HBNI. We have Dr. A.K. Anand, Former Director, Group Director, BRC, Professor B.K. Maiti, Professor B.K. Nayak, HPAR, S.K. Ghosh and others in our HBNI Council. And my colleague, Navin Kumar, he has organized from HBNI side along with Raghvendra Tiwari from BRC. I thank them all for joining these functions and making this occasion a beautiful occasion to celebrate. I welcome my colleagues from HBNI as well as from BRC and my dear students from HBNI as well as from BRC and many dignitaries who are present here digitally and also online for joining this function. In fact, everybody knows that engineers are pillars of our society. In fact, because of them, we have got many infrastructures and technologies which we are enjoying for our comfortable and meaningful living. And to salute the contributions made by engineers to the societal progress, National Engineers Day is celebrated on the 15th of September each year in memory of India's engineering icon, Sri Moksha Gundam Visvesvaraya. He was a highly disciplined, devotional, and hardworking engineer and well known for his sincerity and time management. He immensely contributed to various areas, especially in civil engineering, which includes roadways, dams, entry-flood systems, and due to his immense contributions in development of various facilities in India, in various parts, not only in Karnataka. He was awarded the Bharat Ratna by the Government of India. On this Engineers Day, I, on behalf of HBNI and my own behalf, congratulate all the engineers who are present here and those who are serving the evenings at various places for their contributions for development of nuclear energy programs and other allied things. And I once again thank you all and welcome for this function. Thank you.
Thank you, Professor Nayak, sir. May I now request Professor U. Kamashi Mudali, Honorable Vice Chancellor at HBNI, to present a bouquet of flowers. Welcome the chief guest. Sir.
Sorry.
Thank you, sir, for doing the honors. And may I now request Professor U. Kamachi Mudali, Honorable Vice Chancellor, to deliver the opening address. Sir. Good afternoon, Dr. Devasis, Professor Naik, Professor Tiwari, Naveen Kumar, and senior colleagues from DRC, and other online participants from HBNI who are joining for this Engineers Day lecture, special lecture by Dr. Devasis Padacharji. All of us know that most of you are here from materials background, that the government of India instituted a national scheme policy in 2017 to enlarge the scope of production of steel in our country. Steel is the primary metal that is used in industry. Anywhere you go there, 90% of the construction material is steel. Currently, the country is producing roughly about 140 to 150 million metric tons of steel. But the 2017, the National Steel Policy envisages that by 2030, we should have around 300 million metric ton capacity for the steel production. If accordingly, that much iron ore will be excavated, mined, and beneficiated, then we will also have the steel products coming out from these plants. At the same time, if you look at the Sustainable Development Goals, there is a resolution called Agenda 2030, which was passed in 2015 by the United Nations General Assembly, where 17 SDG, that is Sustainable Development Goals, have been instituted by the UN General Assembly for all the 154 member countries, with 169, I think, targets to fulfill. If you look at most of them, some of them are like the climate change, clean energy, clean water, but some of them are industrial production, smart city, infrastructure development. So you can see the contradiction that you have to make a lot of production of metals which are required for building any industry or for any infrastructure or any purposes. At the same time, you are also maintaining clean environment, climate change. Energy has to be, also to be renewable. Many concerns, you can see the conflict in the requirement. So by 2030, our country is going to produce 300 billion metric ton of steel. That means currently whatever CO2 that we are producing is going to be almost double. Normally, the steel industry produces, according to the statistics, about 68% of the CO2. By you consider 100% from the entire ecosystem, 68% is coming from the steel industry. Indian steel industry is the second largest in the world. We produce today about 150 million metric ton. Number one is China. China produces around also 250 million metric tons. So if you look at the per capita consumption of steel, we are just about 75 to 100 now. We are trying to reach 100 kg, whereas the world average is around 260, and China is more than 3 to 4 times of the world average. So this is the way the steel is consumed, and steel is going to be produced in multiple numbers, not going to be just incremental growth. That means the carbon dioxide, the primary all of you know that in the plasma furnace, if you burn the iron carbide and coke, you are going to produce enormous carbon dioxide. So every ton of the steel that you produce, almost twice 2 tons of CO2 will be released to the environment. So from 150, if you are going to 300 billion metric ton by 2030, it's going to be causing so much of enormous CO2 production, and we cannot meet the climate change goal that is set by the United Nations General Assembly, because our country, every country has to give a report card annually. So how are you going to solve the problem? See, today it is impossible for telling the steel industry that not to produce, because it is required for the economic growth of our country. Today, whatever 6 to 7% you want to go to double digit, 10%, 12% of economic growth, we will have a lot of production of steel. That is a major metal that can be commercially, getting your value for the economic growth. So all the steel industries have to adopt a lot of processes that will somehow reduce the CO2, or somehow that they will capture and they will take care of the CO2 for useful purposes. And how this value addition will be done, how they will take care of the entire ecosystem, right from the mining to completing the product manufacturing. So this is always a big question, and Tata Steel being one of the leading steel companies are the right people to give us some idea about by 2030, when the country is going to produce twice of the steel that we are manufacturing today, how we are going to face this CO2 problem and the climate change problem and clean energy production problem. This is the biggest question today. So I thought that for the engineering, the best speaker who can give us some idea on this is Dr. Devasis Bhattacharya, who is a very close friend for more than 2 decades, and he is a leading material engineer in the country, and is the #1 person in Tata Steel who is taking care of the entire technology and R&D. To speak to us maybe for another 30-45 minutes, and which will be definitely an eye-opener for us to know how the climate change will be in 2030 in the scenario of increasing steel production. It also demands that we should go into innovation. We have to have a lot of new technologies, like steel production, a lot of like the DRI, direct reduction process. People are talking about electromagnetic, but the quantum of steel that you will produce will not match 300 million metric ton that you are planning for 2030. But you can try to also use, with respect to energy and CO2 elimination, you can use hydrogen in one of the topmost topics that we discuss every day. Hydrogen production, hydrogen storage, hydrogen transport, hydrogen that can be applied in the actual industrial processes. I'm very proud to tell you that Tata Steel has already implemented the introduction of hydrogen up to 40% in their energy, replacing the conventional coal. And that is giving a very valuable result, I was told, and it is going to be embarked into all the steel plants, not only in their Indian industries, they also have the presence of steel plants in the Netherlands and UK and other places. I'm sure that this lecture will give us a lot of information, a lot of knowledge on this management of steel technology by 2030 by our country, India. Thank you so much, Dr. Devasis, for accepting our invitation and coming over here. Looking forward to have more interactions with HBNI and BRC in future. Warm welcome to you. Thank you.
Thank you, sir. Thank you for your encouraging words, and thanks for emphasizing the, I hope I'm audible. Thanks for emphasizing the release of CO2 during steel production and importance of hydrogen in the near future and beyond. I'm sure your thoughts will inspire many of us to work in this direction. Thank you, sir. Dr. Devasis Bhattacharya does not need an introduction to many of us in this audience. I'm sure during his visit I could see that almost everybody is familiar with him. He's a known name. He's a very well-known personality in the field of material science. Yet, for the benefit of many of our participants, those who are participating through YouTube or those who are online also, I would request Dr. Raghvendra Tiwari, Associate Director, Materials Group, to introduce the speaker to this audience. Thank you, sir. Please.
Yeah. Good evening to all of you. And it's indeed pleasure to introduce Dr. Bhattacharya. And I think it's okay because
Online.
Achha. So it's indeed a pleasure to introduce him. He's our speaker for that, and I think there are many things are common. I found few more today after. See, myself and Dr. Awasthi were the hostel partner for him in late 80s. So he's. How many of you are here from the Jadavpur? Can you raise your hand? 1, 2. See, these many people are from your detail. He is also from Jadavpur. Then he has gone to IIT Kanpur for finishing his MTech degree, and then to University of Cambridge under the very prestigious Nehru Cambridge Scholarship. And he carried out a couple of postdoctoral fellowship also. So Rolls-Royce Technology Center, Cambridge, he has gone. Actually, I have gone to the Rolls-Royce Indianapolis. And another one from the University of Birmingham, US. That is where Dr. Dinesh was. So there are many things you have common with the other DA fellows. Okay, and then he later on joined Tata Steel, and he has joined Tata Steel as in the R&D function in 1996 and headed the function of Chief Research and Development and Scientific Service between 2002 to 2009. Then he moved to Tata Steel Group based in Netherlands and in Europe as the second second in command in the steel research person. Then in 2017, he came back and joined back the Tata Steel Group, back as the future. They are now, after Tata Steel is stretching their wing beyond the steel production. So they are going, stretching their thing, and one of the remarkable was their use of graphene, production of the graphene. I think within 3 years' time, you have reached the second or third in the production, if I'm not wrong. And but now, if you look on the top producer across the world, Tata Steel started coming in the some of the railway brakes are very big. So they're very remarkable growth. By any standard, this is a reaching the world notch. Knocking the world standard is not an easy job, but they have achieved that point. And main pioneering person was Dr. Bhattacharya. And he is now expert in the development of material, decarbonization technology. And he has 60 international papers, 7 edited books, and 40 patents. So this is again another feather in the cap. And he is a fellow of course, National Academy of Engineers and Indian Institute of Metals. But he is also visiting professor for the Imperial College London, Ministry of Warwick, UK, and Ministry of Science and Technology, Beijing, China. So all these are coming in the area. So now I will not. This is very big. So if I go on, I will eat in his time. So rather me speaking, let's listen from the speaker. Thank you.
Thank you, sir, for introducing the speaker to this audience. May I now request Dr. Devashish Bhattacharya to deliver the talk. Welcome, sir. Thank you.
Professor Kavachi Mudali, thank you very much for this very kind invitation. I'm honored, not only by the invitation, but with the opportunity that I get to be present here inside a campus of which really is a temple to science and technology in India. It's an honor to be. It's a lifetime honor to be here. And thank you for showing me around in one of the research groups. Dr. Tiwari, great to meet you here. As you mentioned, there are more things in common, and just one of the few things in common, ladies and gentlemen, is that I have used your scooter without knowing that it was your scooter in IIT. You just found out. A bit too late, but better late than never to find out who the owner of the scooter was or is. Dr. Naik, great to meet you, and I'm sure our interactions will continue into the future. We've discussed about how we can have workshops and look at opportunities for both great institutions to collaborate. Dr. Kumar, thank you for organizing this, taking us and hosting this day. And again, I'm extremely honored to be here today, and thank you for being here for this talk, ladies and gentlemen. So I will talk on decarbonization of the iron and steel sector. And I think Dr. Kamachuda has given a very succinct, just introduction to the topic, which means a few of my slides are taken care of, which will make the talk shorter. But before I start, I would give a brief introduction to Tata Steel's R&D, very brief. I won't bore you with the details too much. Tata Steel, I don't think you need to have an introduction to. It's known, right? In India, I don't put slides on Tata Steel, right? But I think not many here would know that an industrial R&D is not just testing lab. It's more than just a testing lab. Our purpose in technology and R&D is to deliver new to the world products and services, which are to the benefit of our customers and makes us the most preferred supplier to any customer in any sector. And I'm sure it is same for any organization, even a research organization. Every organization has a stakeholder and you would want to deliver to the best expectation of the stakeholder. Second is to deploy new technologies addressing sustainability. And that's really the core of the discussion today. And to build industry-leading technology management processes and capabilities. And this is not only our building internal capability, but also leverage external ecosystem as a part of our overall capability and help in accelerating our journey towards new technology deployment. And this is roughly what we cover in our technology and R&D vertical. We look at materials from mineral beneficiation through the processes of manufacturing, extraction, manufacturing, forming, joining, application development of not only steels, but also non-steel materials, as you have mentioned, Professor Tiwari. It's not only graphene, but also fiber-reinforced polymer composites and advanced ceramics. And then, of course, deep decarbonization and value from waste. On the other hand, we also, and these are the main core technology development areas. And there are support areas such as quality assurance and failure analysis. And my specialization is failure analysis. I work with Professor John Knott and Dr. Julia King in the past, and of course, customer-driven product development. We have about 860 employees in technology and R&D. So we not only have internal strength in having our PhDs and master's degree employees, we also have technology leadership development programs which continuously develop our people and give them exposure across the world. We do realize that as technology changes more rapidly, we cannot keep up with having all capability inside. And it is changing so rapidly that there is also redundancy of capability. So we have decided to spread our wings and go outside. Have open innovation centers, which we have opened a large number of satellite R&D centers. We started with India. We have one in IIT Madras, one in IIT Bangalore, ISM Dhanbad, and each is in a particular area. So IIT Madras is on advanced mobility, where we're looking at advanced mobility. We're not just looking at high-strength steels for cars. We're looking at hybrid materials for extreme lightweight. We're looking at hyperloop transportation and things like that. I think the announcement will have just come out. It's 3:30, past 3:30, so it will have come out. We are opening two R&D satellite R&D centers in the UK. One at the Henry Royce Center for Advanced Materials in Manchester, and one on sustainable design and manufacturing of materials at Imperial College. When we have visiting scientists and professors, and from our common time, Professor R.K. Day, Professor Ahindra Ghosh, Professor Lahiri from IIT Bangalore, they were all visiting professors, spending 2 to 3 months in a year in our labs. So that's roughly to give you a picture of what we do. We just don't do testing. Right? And just to prove that we just don't do testing, this is our intellectual property generation, number of patents that we file, which is going into more than 100 per year. So, which is not bad for an industrial laboratory. The important part is not coming for some reason. It's shifted a bit. Yeah. It should be full page. control there. Anyway, while this is going on, let me not waste my time. In terms of focus on technology development,
Thank you.
so yeah, that's better. Thank you. So we have decided to focus on technologies which we are going to drive fast. As you, the whole field of technology is quite wide, and we need to focus. And therefore, we have decided to treat 3 areas as technology leadership areas in which we will lead the world. If there are no examples in the world, we will set examples. And these are utilizing low quality raw materials, which includes value from waste. It has carbon capture and utilization. The name is obvious. It has hydrogen, which includes generation, storage, and transportation of hydrogen to make it cheap and clean. Advanced mobility, which includes use of hybrid materials, use new mobility technologies I mentioned before. Water is a big thing in part of SDG. And as a steel company, we use a lot of water, mainly for cooling. But then as a part of cooling, it also entrains in itself a lot of impurities, including color and particulate material, and some chemicals which are not very friendly, such as cyanide. So we need to be able to go to zero water discharge through technological interventions that remove all these contaminants. Coatings, steel corrodes, looks bad, and therefore you use coatings traditionally zinc, and Dr. Kamaji Mudali is perfectly aware through his corrosion involvement of what we do in corrosion. But then giving a coating also enables us to give steel functional capabilities, such as antimicrobial properties, such as hydrophobicity or hydrophilicity, depending on what the application is, so on and so forth. And of course, the last one is advanced process control, use of AI and ML. So I don't know how many of you know steel. You don't need to know, but it's a very long, complicated process, starting from raw materials to the finished product. And you see the finished product only when you touch the surface of a car. You don't see the iron ore from which it came, but you want the car to be very, very shiny and defect-free. To get to that stage, it has gone through thousands of processing steps. And eventually, the material that you get needs to be defect-free. Just as an example, the coil that a car maker gets from a steel company is roughly 0.8 millimeters thick, with tolerance in microns, is about 1.2 to 1.8, depending on what the component would be made out of. It is, if it is 1.8, again, the tolerance is in millimeters, in 1.8 meters. It's about 6 kilometers long, and there cannot be a single defect in terms of visible defect on the steel. That's the expectation. To get to that expectation, of course, there are a lot of rejections that happen internally and externally. We intend to reduce those defects to zero. And it's only possible when you know exactly what the operating window is in each of those 1,000 processing steps. Humanly not possible. And therefore, humanly, we don't get zero defect. But it is possible through training, artificial neural networks, using AI, ML, and sensors. So that's the final area of focus in our technology development goals. Just to give you some example. Is this one? No.
काम करेगा
Yes. Fantastic. Yeah, it works. So just to give you an example on how we use low-grade raw materials of kali from waste, this is manganese ore. We have iron ore, we have coal, we have also manganese ore. From where we make ferromanganese for use as an alloy in steel. But as in any ore, it has rejects. And we throw away those rejects. But we could get value out of them. So we have developed a technology for generating high quality gamma manganese oxide from the reject manganese ore. We have, this is a pilot plant facility that we have created at Sikri, Raikodi, and it is now producing at 5 kilograms per day of battery grade gamma MnO2 from our reject manganese dioxide, and is now available for shipping to battery manufacturers for use in LMO cathodes. Right? This is a byproduct from our coke plant. And this is not, I usually use this joke to non-metallurgical audiences. This coke is not for drinking, but this is a metallurgical audience which I presume knows what coke is, right? So it's a product of coal that is used in blast furnace for iron making. In the process of making coke, there's a lot of gas that gets generated. And one of the visits that I had today, we had an inkling of a potential project that we can do together with this coke oven gas, which has a lot of methane and carbon monoxide, and perhaps can be used to produce long chain carbon nanotubes. Right, so that's potential area forward. But it also produces carbon, coal tar. Now, normally coal tar is used in a very low grade operation, applications such as use on roads. This same coal tar can be used to make needle coke. When needle coke goes into electrodes for electric arc furnaces. Electric arc furnaces are going to have huge growth in India and abroad, and all needle coke today comes from China. We don't want to be dependent on imports, right? So for India's sake, we need to produce needle coke internally, and this is a source of needle coke. And we have set up a pilot plant which is now operational in Jamshedpur that produces needle coke from coal tar reject. This same needle coke also gets into anode for electric vehicle batteries. And then we are at the pilot scale for making carbon fiber, which is structural grade carbon fiber from this coal tar. And we have gone from lab scale to pilot scale. There is no pilot scale facility available in India. There is one in NAL, but that's from petroleum, yes, polyacrylonitrile, thank you. But we need to produce from coal tar. So we are doing this work in Italy. The result is this. So we used our cathode material from our manganese ore mines and coal tar sourced needle coke into batteries. And this was a battery we actually produced fully. And it went into the scooter, which we ran on the 3rd of March this year. You can see the parameters here are not very far from commercially available similar to 1700 batteries. Of course, these are early days. As we move up in scale, I'm sure our material will match commercially available material, which will make much of the battery material indigenous. The entire anode can be indigenous, the part of the cathode can be indigenous, and therefore lower cost and strategically better cost, using rejects. Let's move on. So just to show what sort of research and technology development we do under those technology leadership verticals. They are not copying others. They are fundamentally new technologies for the world and essentially for the benefit of the steel sector and for the nation. Let me come to carbon dioxide, which is the crux of the talk. And whenever I give a talk on decarbonization, there's always someone in the audience who asks, is it really a problem? I mean, Earth has been hot before. Earth is getting a bit warmer. So what? I mean, is this really a ruse? The next few slides will prove, at least for this audience, for now, that it is not a ruse. It's a fact, and we need to get some action done. So the Earth has seen multiple mass extinctions before, and after every mass extinction, the Earth has come out better. It has come out with more organisms. It has come out with different organisms. In fact, had those 5 mass extinctions not happened, human beings, us, we wouldn't have been here. We would still have either the dinosaurs or some lower form of animals on Earth. So thank you for the mass extinctions. But then, what happens before a mass extinction is the number of species and families and the genuses and families start getting eradicated from Earth very quickly. And this is what we are seeing today happen. If you plot the rate at which various families of animals are getting extinct across fish, reptiles, birds, and mammals, they all are getting extinct at a faster rate. Yes, the Earth has been hotter before. So, for example, in the dinosaur era, which is my name, dinosaur era, it's not called the dinosaur. You know, it's Jurassic and all that. The Earth has been definitely hotter. In fact, the temperature of the Earth is directly proportional to the carbon dioxide in the atmosphere. And at the same time, when the dinosaurs were around, so around 60 million years ago, when they became extinct, just before that, there were alligators in the Arctic. Right? Carbon dioxide was around 1600 ppm. Then it dropped. And as the Earth cooled down, dinosaurs became extinct. That was the mass extinction at 60 million years ago. And then after some cycles, over the last 1,000 years, the temperature has been pretty steady, and the carbon dioxide has been pretty steady at around 250 ppm. But it's today, just the last few hundred years, it is going up, and it's last month it was measured to be around 450 parts per million. So it is definitely going up. And as geological history shows, temperature rise is proportional to carbon dioxide rise. So temperature will go up. Human beings came when the temperatures in CO2 were low. Well, with these temperatures, the dinosaurs may come back, but definitely it will be very difficult for human beings to survive. Right? And this is a more recent history of only 800,000 years. As you can see, CO2 has always been below 300. It's the first time in 800,000 years that CO2 has crossed the 450 mark today. Yeah, it shows 420, it's actually gone up to 450 now. So it's happening. The temperature rises that we're seeing is proportional to the CO2, and the CO2 increase is happening. It's a recent phenomenon linked to our industrial activity. So, ladies and gentlemen, Earth will take care of itself. It will probably come out better off with more animals, with different vegetation. Problem is, we won't survive. So all the actions that we have to take is for us. Yeah, the Earth definitely will take care of itself. So let's now talk about what we can do. So this is very common, right? Everyone wants to say that the carbon dioxide emission must go down to 0. And only then you contain yourself to 1.5 degrees centigrade increase from the average level of about 250, 300 CO2 level. That's not going to happen. Today we are giving out about 34, it's not written down here, it's in the next slide. Today we are giving out about 34 gigatons per annum. And this number is increasing. And you'll see next year's result, it will probably become closer to 40 gigatons. So 1.5, forget it, by end of the century. We have to struggle to get to 2, contain temperature rise to 2 degrees centigrade, which means we have to contain CO2 to 50, man-made CO2 to 50 gigatons. Gentlemen and ladies, we are already at 34 this year. And do you think in next 75 years we'll be adding another 25? We'll be adding more. And if we don't do anything, we'll be adding even more, maybe 100 gigatons. If it's 100 gigatons, the temperature will go up to anywhere close to 3 degrees centigrade. And anything more, it's closer to 4. And this is a pictorial depiction of how vegetation gets affected, how barren the landscape will be, and how difficult it will be for human beings to survive. So the point is, we need to contain our CO2 emission to anywhere between 0 to 50 gigatons. Today we give out 34 gigatons. This is annual figure of last year. The main culprits, man-made culprits, are energy, transportation, industry, agriculture is anywhere there, and others. So main are electricity, transportation, agriculture, and industry. We know very well that energy will take care. Energy, there is a path forward because there is now technology available for wind, for solar. Prices will come down. As you can see, the renewable surpasses. Generation has surpassed, the prices have come down for renewable energy. And over the next 10, 15, 20 years, it's going to be more so. Automobiles have a roadmap forward through electric vehicles and hydrogen. Right? So they will take care of their carbon dioxide footprint. What will not happen so easily is the industrial sector, and especially in the industrial sector, 2 or 3 industries which are very difficult to handle. One is steel, second is cement, third is aviation. You can't carry hydrogen and fly a long distance plane. Right? You can't carry batteries, heavy batteries, and carry also people in a plane. You just carry batteries in it. So just to give an example, out of the 34 odd billion tons of carbon dioxide, steel contributes about 3.6, which is about 9%, 10% of the man-made CO2. Now, as I said, other sectors they have a roadmap. So by 2050, they will reduce 7.7 if they put new technologies in place. If steel doesn't do anything, steel production will increase, CO2 will increase, it will become 40% of man-made CO2. Now, our children will not accept that. Our children, today it's already happening. European plants, steel plants are under immense pressure to close down unless we reduce our CO2 footprint. They don't care if people go out of job. They care as long as CO2 is not emitted by those plants. Yeah. So this pressure from the people is going to be sustained. And at 40%, you can understand what the pressure would be. So we need to do as a sector, and I mean, I'm sure same discussion happens for steel, cement, and aviation. We need to do something today to ensure that the CO2 footprint of the sector goes down. Had there been a technology solution, just like in automotive and in power, people would have put those roadmaps down and actions would have been taken. There is no solution. And the reason is this: as Dr. Kamachi Mudali mentioned, the world makes about 2,000 million tons of steel. A large part is made using blast furnace. And a small portion is made using electric arc furnace. The blast furnace uses iron ore, uses coke, and the coke produces the iron ore. Coke is carbon dioxide comes out. And that gives the largest CO2 footprint. Electric arc furnace can use scrap. Scrap is not oxide. It just needs to be more melted. And if the electricity is green, steel produced using electric arc furnace is green, right, largely. But only a small amount of scrap is available in the world, and therefore only a small amount of steel is produced through electric arc furnace. So our target for decarbonization is blast furnace and its route to steel making. This is a 101, one slide primer on steel making, on iron making. Okay. So you have coal and iron ore that goes into the blast furnace. There is some coal becomes coke, iron is agglomerated, goes into the blast furnace, CO2 comes out on the top, and you get liquid iron from the bottom, which goes into steel. The crux of the matter is this. Iron ore, which is iron oxide, is reduced by carbon to make CO2. So of course, to decarbonize, it's very simple, take away carbon and use something else. So this is called carbon direct avoidance. Can we do that? And of course, we have mentioned hydrogen. So you can have alternate fuel, which is hydrogen, into the blast furnace. If you still have some carbon dioxide coming out, you can react that carbon dioxide with hydrogen, make some molecules, big molecules, trap the CO2, so carbon capture and utilization, and you've solved the problem. Conceptually, yes. And if you still don't have a solution, you can use scrap. You can use alternate reduction technologies. So what is the problem? The problem is this, it's a rainbow. I'll need some time to explain it, but it gives in one shot what the problem is. So this is all technologies available for the left-hand side of this plot, which is carbon direct avoidance, which means, can we avoid carbon in the blast furnace? So can we replace carbon by something else? So this has three sections. Makeshift, which means you have the current process and you make some tweaks in the current process, which is easy to do, and you reduce the carbon. Retrofit, you add something to the current process, some equipment, and you reduce the carbon. Transformational is you use a completely different technology for reduction. As you move into outwards, so blue to pink to green to gray, you go up in maturity of the technology. So from lab to pilot to demo to commercial scale. As you can see, all the commercial scale, near commercial scale technologies are makeshift, which means you do something, you tweak something in the existing blast furnace process. So you can add scrap, we have already discussed that. You can add biochar, which is from vegetation. You can add hydrogen in the blast furnace, which we have already done. And it's ready for next upscaling when hydrogen is available in the, so therefore it's at the demo scale. And you can add coke oven gas, which has 50% carbon monoxide. So it's the same carbon monoxide, you put it into the blast furnace. So that's also in the demo scale. But it also means, if you look at the color coding, that the emission reduction potential is only less than 25%. You cannot take care of all the carbon using these technologies. You still have the need to use carbon in the blast furnace in spite of putting this full. If you put 100% hydrogen through the 2 years, you will still need coke in the blast furnace for other purposes. I'm not going to do that. Retrofit, there are not many technologies in the retrofit area. The easy melt is one where you do dry reforming of methane. And this methane can come from coke oven gas. You do dry reforming, you get carbon monoxide. And basically you get carbon monoxide. But it's a technology which is at a demonstration pilot scale, longer term, and has 25 to 50% efficacy in carbon reduction. All the higher reduction potential technologies are all transformational. You will need new furnaces. So molten oxide electrolysis. There's a company called Boston Metal, which came out of MIT. Upscaling is extremely difficult. You have electrowinning technologies. We have Helios, which uses sodium as a reductant. Who says hydrogen is the only reductant? And you have hydrogen-based DRI, which you mentioned. And that also is a technology which is moving up in the scale because green hydrogen itself is not available. But still, only 50%. So the point is, this is still on the left-hand side of the previous graph. It means direct avoidance of carbon. You can at best get 50%, around about 50%. But mostly, if you use existing technologies which are easier to use, easier to scale, you'll get 25-ish at best. When we put hydrogen in the blast furnace, we put 40%. You can go to 100% for the 2 years, but you still need carbon. You can do about 12–15% of replacement of the carbon. Similarly, there will be physical limitation, there will be kinetic limitation, there will be thermal limitation to how much carbon they can replace. So the point is, you will have carbon dioxide coming out still, even if you put these technologies in place. Therefore, you need carbon capture and storage. So the carbon dioxide that comes out needs to be captured. And that capture is amine technology, known, you can treat that technology. But how do you store once you get carbon dioxide? You can't just put it in cylinders and outside somewhere. People have tried in the West, try to find geological formation and put carbon dioxide in the geological formation and seal. It's called sequestration. It is still active, but there is no such geological formation known to us yet in the eastern region where most of the steel plants are, eastern region of India. So sequestration is out of the equation now, as of now. So we need to find a chemical way of storing this carbon dioxide. So which means making, say, things like calcium carbonate. But how much calcium carbonate can you make? Right? There's a finite market for that. More prolific would be organic molecules. You can start with methanol, go to ethanol, or from ethanol or ethanol, you have whole other routes for longer chain organics. You can make syngas and use that again, or you can do mineral carbonation of slag, make cementitious aggregates, or you can make organic carbonate and solid carbon, you can make carbon nanotubes, etc. But just now look deeper into the problem of carbon capture and use. Suppose you make the simplest of molecules, which is methanol. You will need hydrogen, and for every 20-odd million tons, we talk in million tons. We don't talk in grams or kilos or tons. We talk in million tons. Simply because plants are in million tons, and 1 million ton of steel produces roughly 2.5 million tons of CO2. You can work out the equations there. So this is a 10 million ton plant producing 22 million tons. This stoichiometry. 22 million tons of CO2 will need 3 million tons of green hydrogen to make methanol. Now, how much is 3 million tons of green hydrogen? Today, the world makes about 70 million tons of hydrogen, out of which world makes 3 million tons of green hydrogen, which will be needed to fix carbon from one steel plant in the world, which is 10 million tons, right? 22 million tons. So today it's not feasible even to capture and utilize all the CO2 by making methanol. So let's look at India. Yeah, you mentioned, Dr. Kamaligura, you mentioned India steel production in 2030. I don't know if you had a premonition, but I had taken 2030 as a target because India has taken net zero as a target for 2070. Most steel companies have taken, including us, have taken a target of 2045 as net zero. So very strict and ambitious target, but we'll get there. But we can't get there in 2044, right? We have to start acting now, and therefore we have a roadmap. Our roadmap is to be 1.8 from a level of 2.2, 2.5, it will be 1.8. What is 1.8? Right. 1.8 tons of CO2 per ton of steel. So India by 2030 will produce whatever you said we will produce, maybe 250, maybe 200. We'll say that some of it will not be blast furnace, but there will be some blast furnace. You cannot wish away the blast furnace, so that's the only commercially viable route known. So Let's assume 175 million tons in India will be produced through blast furnace by 2030, which is a reasonable estimate. At 2.3, this is wrong, sorry, this is 2.3 tons of CO2 per ton of crude steel. TCS is not Tata Consulting Services, it's tons of crude steel. My mistake. So at that, so India will make, assuming it's 2.3, India is today way above 2.3. So I'm assuming in the next 6 years, all the steel plants will put in measures, small measures, reducing coke rate and come to 2.3, which is itself a challenge. If it does, it will produce 400 million tons. If it has to come to 1.8, suppose it makes 1.8, it will make 315 million tons of CO2, which means you have to abate 85 million tons by 2030, you have to abate 85 million tons of CO2. 85 million tons. Right? Now, we have just seen that the technologies that are at high TRL levels have lower efficiency of carbon replacement. Right? We saw it in the previous graph on the left-hand side, purple dots. So assuming that, given all the efficiencies and inefficiencies in this, 5% of carbon direct replacement will happen. Which means 20 million tons will be taken care of by the new tweaking technologies, scrap, biochar, etc. You will still have 65 million tons to be taken care of by 2030 through new technology. Because 1.8 is the target. 65 million tons will mean hydrogen needed to make just methanol, which is the simplest of molecules. 9 million tons of green hydrogen will be needed by 2030. And if assuming, I'll go to some more calculations, assuming that the cost of green hydrogen is $2 per kg, which it is not. You know what is the cost of hydrogen? 6, 7, 8, anything there. Assuming if it comes down to $2 per kg, it will be an extra $18 billion on the Indian steel making. Now, that 9 million tons of green hydrogen is what the global hydrogen production is predicted to be in 2030. That will be needed just to come to 1.8 in India. And it will add $100 per ton. So the steel that you buy will be 9,000, 8,000, 9,000 rupees more expensive per ton. Right? Just to show you some more. Forget it, it looks like a busy slide, but just look at some of the numbers. Around India. That cost will be around $5 billion. That is for 45,000 crores. So just carbon capture. Hydrogen, to produce 9 million tons, as I just said, will need 4.5 lakh crores, 160 acres, and 60 gigawatts. What is 60 gigawatts? Delhi, Calcutta, Bombay, Madras put together is about 15 gigawatts. 4 times these 4 cities will be needed to produce enough green hydrogen for 1.8, not 0. And then you have to have a methanol production unit, which hopefully the steel industry won't do, but somebody has to do in the country. And that's an additional 4.5 lakh crores, provided you can sell all that methanol. That 40 million tons per annum of methanol is way above what the world sells today. So the point is, you'll not solve the problem by just making methanol, even if it is expensive. Cost of steel will increase. You will need to produce green hydrogen in those numbers, and methanol is not the only solution. You have to go to find other solutions because there's not enough capacity in the world to use that amount. You have to make ethanol, you have to make even go to sustainable aviation fuel and things like that, or whatever. And as you go up in the number of carbons in the cycle, the cost goes up. So the search is for multiple levers. If you're going to decarbonize steel, if you're going to attain net zero, even commercial net zero, you've got to find multiple levers. No single lever will survive. Some are the usual suspects. Use more scrap. There's a limited supply. Scrap usually comes back in a cycle of 25 to 30 years. India's steel production has not been so high to bring scrap back in those numbers. The steel mature countries, the more developed countries have that cycle. USA and Europe UK have that cycle in place. And their steel production, that steel growth is saturated, so they're not growing. So it's a sustainable scrap recycling country. India is growing with a low base. India doesn't have scrap. Natural gas or hydrogen-based DRI and EF. So hydrogen has to be green, so that's a limitation. DRI EF route. DRI is direct reduced iron, and EF electric arc furnace. So if you use that route, you need very high purity iron, 67% pure. India doesn't have much, which really is a limitation for this route. The alternative to this is a remelter. And we're getting into technology of steel, so I'll just brush over it without getting too deep. Remelter technology needs scaling up. It is good for ferroalloys, not for steel. So again, it needs technology intervention. Biomass, so biomass was one example, one solution. But how much vegetation are you going to cut and replant for these tens of millions of tons? There's a limitation. Each of these can be used and will be used, but will have a limited effect. You will need new technologies as levers. You will need high efficiency electrolyzers. Today, those numbers for hydrogen are high. The electricity consumption is high because the electrolyzers are not efficient. They're only about 50%, 60% efficient. If you use solid oxide electrolyzers with the heat available in a steel plant, you can use that heat in the solid oxide. I can make the electrolyzer run at 100% efficiency. The cost of hydrogen drops. You can use or look for non-electrolysis route for hydrogen. I'm going to talk a little bit more about that. We always ignore in this whole discussion the need to store and transport hydrogen. We assume hydrogen made is used. When you're using hydrogen in these millions or tens of millions of tons, you just can't assume that there's a direct link. There will be a storage somewhere. Right? I'll talk about storage. And the rest I've talked about. Today we are researching and developing technology on all of these, and we are investing about 200 crores per annum, and that will increase only as our technologies scale up. So we are looking at coal-based methane, which is demonstrated. So methane is natural gas from the coal bed, put it into the blast furnace, see how the blast furnace reacts and how you run it safely. Hydrogen demonstration we did by injecting 40% in the blast furnace. Replacing, we put in coal, pulverized coal through the 2 years. So replace that with biochar, which is green. So all these experiments have happened and we are upscale. We're also looking at non-electrolyzer route for hydrogen. So this is one of the routes we're looking at, which is chemical looping combustion, which uses a catalyst here. Just happens to be iron oxide, but it's in a certain form. The iron oxide is reduced by the blast furnace gas. Blast furnace gas has carbon monoxide and carbon dioxide in roughly the same proportion. Iron oxide is reduced to the lower form of oxide, and carbon monoxide becomes dioxide and becomes rich, and therefore easy to capture. The reduced form of iron oxide comes down and is as a water gas shift reaction. Basically, you put steam, there's a lot of steam in the steel plant. Put steam, the lower form of iron oxide becomes the higher form of iron oxide and goes back into the cycle, and the steam is reduced to hydrogen. You get this is thermal neutral. You need initial thermal energy to start it, after which it generates its own heat to sustain this. So this is at a pilot scale today in Jamshedpur. We're working with Ohio State University to take it to the demo scale. But it will take time. It will take 5-6 years to scale up to anywhere close to plant scale. The hydrogen storage, which we always miss. Today, hydrogen is stored, when we think of hydrogen storage, it's either as liquid, which means you have to cool it down to minus 250 degrees centigrade and keep it at minus 250 degrees centigrade, which is expensive, energy consumption. Or pressurize it at 700 bar pressure, and keeping at 700 bar again is energy. Or you store it as liquid ammonia, minus 35, better than minus 250, but still needs energy to maintain minus 35, and is extremely poisonous. In an industrial atmosphere like us, that's a concern. So we are working with a startup from Israel on a system that is a formate bicarbonate cycle using a catalyst which stores hydrogen in a formate fluid at room temperature, room pressure, normal pressure. It needs about heating up to 35 degrees centigrade only, and a catalyst to liberate that hydrogen. Right? So we are trying to upscale that to 1 ton per day level, which is minor, but it's a technology which is a breakthrough. Breaks the cycle of needing low temperatures, pressures, etc. And you can see the difference in cost that it will bring. This is a carbon capture unit that we have installed in Jamshedpur, which is at 5 tons per day, and now we've been running it for the last 2 years. We've got the data, we know how this works. We're now upscaling it to the next level of about 15 to 20, 15 kg, 15 tons per day. And associating that, linking that up with the methanol for capture. But all this will happen not by itself. As you can see, this needs enormous amount of resource, both manpower and money, to take these technologies forward from lab to pilot to. It will need policy framework. It will need policy framework for steel to be sustainable as a material. As I said, cost of steel production will go up because of green, because of zero, net zero. So we need to have a way to have a level playing field across the world with carbon tax, with border adjustments, I think. And of course, we need to have policies that will encourage material efficiency, fund R&D program for net zero, and so on and so forth. So in conclusion, technologies to decarbonize steel are not yet mature. Net zero is far. Companies will need to depend on both incremental reduction and the near term, and also bet on emerging technologies for the longer term. And of course, decarbonization will need technology, money, land, and conducive policies to be in place for that to happen. Thank you for your attention. I hope it was.
Hello. Now it's already open for questions. I'm sure that many of you are eagerly waiting to ask the questions, but with the paucity of time, we'll restrict to 2 to 3 short questions. Yeah, please identify yourself and.
And Shobhit Bhattacharya from Technical Physics. So, can you comment on the safety aspect of this hydrogen?
Yeah, very good question. In fact, whenever we do a large, small or large, when we do an experiment or technology development of hydrogen, that is the first concern we have. So just to give an example, when we did the demonstration of hydrogen in a running blast furnace, we got the hydrogen in cylinders in 200 bar pressure, and that was pushing hydrogen in. But the hydrogen was not going in at 200 bar pressure, it stepped down. So So there was a lot of piping involved. And we needed to make sure that the piping is leak-proof. If you put hydrogen and then try to find out leak-proof, it beats the purpose, right? So you need to put something else. So what you put, hydrogen is the lightest gas and the smallest atom. So you put smallest molecule. So we started by putting air, and there were leaks. So we blocked up those leaks. Then we put helium. And after we thought we had done a very good job, when we put helium, 14 leaks came out. Right? And how do you even test for helium? So there was a whole technique for that. I'm not going into the details. And then we made sure that at least for helium it is fine, and helium not being far from hydrogen, we assumed. And of course, we did have the same apparatus as for testing helium when hydrogen was being pumped. Make sure that leaks are at least not happening. So yes, so that's one. The process for processing of hydrogen, or the process of transferring hydrogen, we take safety precautions. Even when the hydrogen comes in to the plant, how do you store in bulk? There is safety issues. There are safety issues involved. You only allow a certain amount of hydrogen to come in. The rest you keep away from population and plant. Yeah, so we take multiple actions, precautions to make sure that you're safe when you're dealing with hydrogen. Yeah, I just gave you a few. Yeah, Dr. Rose.
I was thinking, it is quite impressive, this format bicarbonate cycle.
Yeah.
I was wondering how much specific volume you use for 1 unit of hydrogen.
Yeah, so that table didn't have it, right? I dropped it deliberately. I dropped it. Specific volume is less today, but that technology is also going through its cycles of improvement. It is getting close to ammonia, the efficiencies of ammonia. Yeah. But it will not be close to liquid hydrogen. Yeah, but ammonia, yes.
One more question at most.
I mean, liquid ammonia.
I will tell you.
Try from mechanical. One of the methods of carbon capture you're mentioning about artificial photosynthesis. So, what is the state of the technology?
Very, very, very low TRL. That's a simple answer. A lot of groups have been trying artificial photosynthesis for a long time, including MIT. But nature does a much better job than humans. Photosynthesis.
One last question.
So my question is that you discussed about you move to the blue hydrogen part because the green hydrogen production, from urgency point of view, it's not feasible. But if we talk of 2046 or 2070 net zero targets, financially, cost-wise, is it more feasible to invest in setting up blue hydrogen, let's say, facilities, or investing in green hydrogen facilities that may prove fruitful, let's say, at 2050?
So it is very difficult to foresee the future, but what we conjecture today is that there will be no single technology that will provide all those numbers, large numbers. There will be a bouquet of technologies, and some we probably are not even working on today. And some of these that we are working on will not even work tomorrow. But there will be a bouquet of hydrogen generation technologies, hydrogen storage technologies, simply because the numbers are so big, no single technology will work. So, and some of them will be green, some of them will be blue, some of them may be pink. Yeah, you know what is pink. Yeah. So I think we need to be open to any color of green other than gray, any color of hydrogen other than gray. All will coexist. Okay, sir. Thank you.
So
thank you, sir, for covering such a vast spectrum of topics and so nicely in less than an hour's time. And now it's I request Professor Kamal to present the moment of the chief guest as a token of our appreciation. Thank you, sir. So this brings us to the end of today's program, and it's my pleasure duty to propose a vote of thanks. First of all, on behalf of HBNI and our Research Center, I thank Dr. Devasis Bhattacharya for accepting our invitation and delivering a thought-provoking talk on this occasion. In fact, sir, it covers such a vast spectrum of topics in such a short time, so literally. And in fact, when I was going to the newspaper cuttings, particularly on this ingenious day, the topics which are mentioned were like active pharmaceutical ingredients, electrical vehicles, AI and ML, global warming, climate change, sustainable development. Practically, you have covered the entire spectrum in today's talk. Thank you very much. And I'm sure myself and my colleagues, those who are present here and those who are participating online, they have benefited immensely from your inspiring talk and would like to implement the ideas shared by you. And this will be a good review to Sir Vishweswarya, the legendary engineer, on this occasion. Once again, thank you, sir, for your scientifically ambitious, stimulating, and thought-provoking lecture. Thank you, sir. I would also like to thank Professor Budri, Dr. Naik, Dr. Rajendra Tiwari, Commissioner of US Engineering Sciences, Professor R.P. Grover, Dr. A.J. Anand, and my other senior colleagues, present online and offline, for spending their valuable time to be with us. I would also like to thank all the participants for their participation. And last but not the least, I would like to thank my colleagues in Materials Group and HBNI for providing all the logistics for the event. Thank you. Jai Hind, Jai Bharat.
Thank you. Thank you. Thank you.